In the next few videos, you'll see a few different approaches to finding a minimum spanning tree of a weighted graph. Now, a minimum spanning tree is a spanning tree of a weighted graph, that is, it's a subgraph containing all vertices of the original graph so that the subgraph is connected and has no cycles, but such a spanning tree so that the total edge weight is minimized. So for example, here is a graph. One spanning tree is the graph induced by those edges which are in red. So this is a tree which spans all vertices of the original graph, but it minimizes total edge weight. So we use a tree here because this means we're using the least number of edges in order to connect all vertices. But very particularly, we pick even those edges whose total weight is minimized. Now, minimum spanning trees are particularly useful for network design. So for example, say that Kent State University wants to build a campus-wide computer network so that each building has a wired connection to all other buildings. That way, in any one building, you can communicate with someone in any other building on campus. But it costs money to lay wire down in order to connect buildings. And some connections might be more expensive. Maybe construction workers would have to dig up sidewalk cement or redo landscaping, which costs more. But the goal is to connect all buildings on campus using the least amount of money. The resulting network will be a tree, a spanning subgraph which uses the least number of edges to connect all vertices, but even more so that the tree is minimum spanning tree in the sense that the weight of all edges or the total cost of connecting the network is minimized. So these are particularly useful for building a network. Which edges should we use which minimizes the cost to build that network? Now, if all edge weights are unique, then a minimum spanning tree is unique. Otherwise, there might be a few minimum spanning trees for a graph, all of equal total edge weight. Now, it's important to note at this point that a minimum spanning tree, which I'll use MST for short, a minimum spanning tree is not the same thing as a shortest path tree. So we used a few different approaches to construct a shortest path tree. So for example, you saw Dijkstra's algorithm was one approach. A minimum spanning tree minimizes the total edge weight of all edges included in this tree, whereas a shortest path tree gives the shortest path from a single vertex to all other vertices. So it minimizes the sum of all edges along that path. So for example, why these are different. Let's say we had the following small graph. So just 3 vertices and the edge weights, say 4, 5, and 6. And let's compare this to a spanning tree which we would create on the same graph. Same vertices, same edges. A minimum spanning tree would include only these edges 4 and 5, but not this edge 6. This is the only spanning tree which covers all vertices and minimizes the total edge weight, which is, in this case, 9. A shortest path tree, if we were to root, let's say, our shortest path tree at this vertex, the resulting tree that we would obtain would not include this edge 5. We would find that we could get to, let's say, vertex B in 4 steps and vertex C in 6 steps, and this is minimal. Whereas in this graph, this is a minimum spanning tree, so we minimize the total edge weight, but the path from A to C, which remains in the edges that we kept, is of length 9. Whereas here we kept the minimal path from A to C, which is of length 6. So a common misconception here, or confusion, is mixing these two ideas. So a minimum spanning tree and a shortest path tree are separate topics. Now, there are a few properties of a minimum spanning tree that will be algorithmically useful. So consider any edge E, which is not used in a minimum spanning tree. We know that this edge forms a cycle with some other edges of the minimum spanning tree. So if this is our minimum spanning tree here, we have some edge which wasn't used in this minimum spanning tree. We know that this edge forms a cycle with the edges that were included in the minimum spanning tree. Now the cycle property states that for every other edge of this one which was not included, say every other edge that E forms a cycle with, the weight of this edge E is greater than or equal to the weight of any of those other edges which are in the minimum spanning tree that E forms a cycle with. And the reason for this is we can just prove by contradiction. Suppose instead that there is an edge E which was not included in a minimum spanning tree, where it has for some one of these edges, let's say this one, for one of these edges, the weight of E is strictly larger than the weight of F. And in that case, we could just exclude this larger edge from our minimum spanning tree and use E instead. And by doing so, we would get a smaller minimum spanning tree, which contradicts that we had to begin with a minimum spanning tree. Now, as a consequence of the cycle property, we also have what's called a partition property, which states that for any partition of vertices, there is a minimum spanning tree that contains a minimum edge connecting them, a minimum weight edge connecting them. So for example, we have here a partition of vertices in green and the other in blue. The partition property states that of all of the edges which connect these two partitions, which starts in one side and ends in the other side, there is a minimum spanning tree which contains that edge that has the minimum weight among the other edges which connect the partitions. And we can prove it as follows. Say we have a minimum spanning tree. If it includes this edge, which has minimum weight compared to all of the other ones, then we're finished. Now, suppose it doesn't. Suppose that minimum spanning tree doesn't include this edge with minimum weight, and it instead includes this other edge, F. Well, we can apply the cycle property that the edge which was not included, E, it forms a cycle with other edges of this minimum spanning tree. But according to the cycle property, the weight of E is greater than or equal to the weight of any edge along this cycle, including this one F. But from our assumption, because E has minimum weight across all edges which cross this partition, then the weight of E is less than or equal to the weight of F. Which means both the weight of E and the weight of F are the same. We can replace a minimum spanning tree and instead of using this edge F, use this edge E instead, which gives us another minimum spanning tree of equal value because we didn't change the sum of edge weights. We'll show a few different ways in which we can construct a greedy algorithm to find a minimum spanning tree based on this property. If we build a spanning tree outwards by picking an edge with minimum weight that connects to a vertex not yet in the tree, then we'll produce a minimum spanning tree. And this is the main idea behind the next algorithms.